Welcome to the introduction to probability theory and statistics. We are in topic 12, analysis of correlation and regression, lecture 3. The first two lectures we have discussed about the correlation in one lecture, regression in the second lecture, and the last part that is a logistic regression which we are going to discuss in this lecture. What is a logistic regression? The simple and multiple linear regression methods we studied are used to model the relationship between a quantitative response variable and one or more explanatory variables. In many practical situations where one is interested in studying relationship between input and output variables, as in regression, the output variable is discrete rather than a continuous variable. In particular, in many practical situations we have a binary output variable. Earlier whatever we explained, one dependent variable and either one independent variable or many independent variables. But now we have a situation in which the output variable is of the binary form. For example, a student applicant receives or does not receive financial aid. The other example, a patient lives or dies during the emergency surgery. So, third example, your cell phone coverage is acceptable or not. In all those examples, the output variable is of the binary form. Further, some of the input variables may or may not be continuous variables. The question is how can one model and analyze such situations? That means two things we are saying, the output variable of the binary form, input variables may or may not be continuous variables. In this section we will address such situations where the output variable is a binary variable, that is a success or failure. In general, we call the two outcomes of the response variable success and failure and represent them by 1 for success, 0 for a failure. For example, suppose that we are studying whether a student applicant receives or denied financial aid. The same example what I explained in the previous slide. P is the probability that the applicant receives aid, and possible explanatory variables includes the financial support from the parents, the income and the saving of the applicant, and whether the applicant has received financial aid before. So, we are defining the P is the probability that the applicant receives the aid. Now, we will assume that these experiments can be carried out at various levels, and a performance of experiment at level x results in a success with the probability P of x. Whatever the success probability P, now we are relating with the level x. Therefore, we are treating a P as the P of x. That means, the problem is to model the conditional probability, that is the probability that y takes a value 1, that means output variable takes a value 1 given x takes a value small x. that conditional probability is a function of x. When the output variable y is the binary variable with the value 0 and 1. So, here we are defining the conditional probability p keeping y takes a value 1, whereas y can take the value both 0 and 1, that is what we are saying. The problem is to model the conditional probability y takes a value 1 given x equal to 1, whereas y is the binary variable which can take the value 0 and 1, fine. In a simple linear regression, we have modeled the mean of y, that is expectation of y of a response variable y as a linear function of the explanatory variable in the form of a plus bx. If you recall earlier simple linear regression model, we had made y is equal to a plus bx plus y is equal to a plus bx plus epsilon. When you take expectation, since epsilon expectation is 0, therefore, expectation of y is equal to a plus bx. So, therefore, when you have a simple linear regression model, the mean of y, that is a plus bx. But now, the scenario is y just it takes a value 1 or 0, 1 corresponds to success, 0 corresponds to failure. Therefore, the mean can be treated as the same as the probability p of the success, because y takes a value 1 or 0 and the probability p is same as the expectation of y. Therefore, the logistic regression model, the mean p is in terms of the explanatory variable y. That means we can relate p and x in the simple linear regression form, that is p is equal to a plus bx, fine. But actually this is not the good model, making since y takes the value binary 0 and 1 and take the simple linear regression model and replace expectation of y by p and p is equal to a plus bx form, that is not the good model. The reason is whenever the b is greater than 0, the extreme values of x will give values of a plus bx that fall outside the range of possible values of p. P is the probability and the probability lies between 0 to 1, but whenever the b is greater than 0, the extreme values of x will give the value of a plus bx that fall outside the range of possible values of p. So, the logistic regression solution to this difficulty is to transform the odds using a natural logarithm. So, earlier we have used p is equal to a plus bx, that is not the good model because so on so reason what I have just now said. Therefore, you create instead of p you create odds. Odds is nothing but p of x divided by 1 minus p x and take the logarithm of odds. So, the ratio p divided by 1 minus p, that is called odds, and Logit is the logarithm of the odds or just log odds. So, now we model log odds as a linear function of the explanatory variable. The same approach what we have done it for simple linear regression, but since y is the binary variable and because of the values are extreme values of x will give the values of a plus bx that fall outside the range of possible values of a b. Therefore, instead of p we are taking logarithm of odds, fine. Not only that, if p cap is the sample proportion, then the odds can be replaced by p cap divided by 1 minus p cap. Whenever p cap is unknown, sorry, whenever the p cap is whenever p is unknown, then that can be replaced by p cap. Whenever p is unknown, p can be replaced by p cap. That is the ratio of proportion of the times the event happens to the proportion of the times the event does not happen. The odds are p cap divided by 1 minus p cap, that is the ratio of the proportion of the times the event happens to the proportion of the times the event does not happen. That is the odds. Therefore, the experiments comes from the logistic regression model. If p of x takes the form of inverse logistic function, that is log of px divided by 1 minus px, that is basically odds. So, the log of odds, that is same as a plus bx. We started with the derivation from the simple linear regression, that is expectation of y is equal to a plus bx, and since y is the binary value, that is replaced by small p, but that is not the good model. Therefore, we created the function called odds, that is p divided by 1 minus p. Then we take a natural logarithm over it. Therefore, the logarithm of odds, that is going to be a plus bx, that is going to be the logistic regression model, which is equivalent p of x, that is equal to 1 divided by e power minus a plus bx times plus 1. Either form is, we can use it, either logarithm of odds is equal to a plus bx or p of x is equal to so and so expression. We call p of x is the logistics regression function. Since the probability is a function of x, we are using p of x. That is the notation for probability that y takes the value 1 given x takes the value small x, that is called p of x. Based on the different possible values of small b, we have the following possibilities. We have 3 possibilities: when b is equal to 0, when b is greater than 0, when b is less than 0. So, either it is going to be a constant function, or it is going to be increasing function and converges to 1, or it is going to be a decreasing function converges to 0 as x tends to infinity. Again, you should remember p is the probability, which is a function of x, because that is a conditional probability of y takes a value 1 given x takes a value small x, that is a function of x. Now, we are going to discuss one simple example. Consider the survey of 300 clients of a car dealer. When asked whether they did refer the service department to a friend, clients gave the enthusiastic answers. There were 234 people that said yes. So, P is the percentage of customers who would say yes to the question among the whole population of the customers from whom the samples are selected. Customers who would reply yes in a simple random sample of size n has a binomial distribution with the parameters n and p. The number of customers who said yes in this count, that is capital X, is 234 out of total 300 people. The sample proportion, that is p cap, we are estimating the p, that is p cap, that is 0.78. So, rather than the proportions, logistic regressions operates using odds. the chances that just the ratio of the two probable outcomes proportions, the chances are just the ratio of the two probable outcomes proportions. If P is the probability of success, then 1 minus P cap is the probability of success, then 1 minus P cap is the probability of failure. So, the odds is P cap divided by 1 minus P cap. From the customer service data, the proportion of customers who would recommend the service in a sample of customers is P cap is 0.78. So, the proportion of customers who would not recommend the service department is 1 minus P cap is 0.22. Therefore, the odds of recommending the service department are given by 0.78 divided by 0.22, that is 3.54. It means there are a lot of times when people talk about odds, they round to integers or fractions. If you round 3.54 to 4, that is 4 by 1, we would say that the odds are approximately 4 to 1. That is, there are about 4 to 1 chances that a customer will tell a friend about the service. In the same way, we would say that the chances that a customer would not recommend the service are 1 to 4. So, this is a very simple example through that we explained the meaning of odds. So, the way we have made the logistic regression function, the coefficients are A and B. When they are unknown parameters, we can estimate A and B. So, you take n such values x 1, x 2, x n, and using the data of sample size n, you can estimate the unknown parameters A and B. You create the likelihood function as a function of A and B. Then you take a logarithm. So, once you have a log of the likelihood function as a function of A and B, you can go for estimating the unknown parameters using maximum likelihood principle. Therefore, they are called maximum likelihood estimates of the unknown parameters A and B. So, this can be numerically, you can get the results in the form of numerical, not the closed form solution. And if the function p of x takes the following form for a constant A and B, then you can write it as in terms of CDF of standard normal distributed random variable. You can write p of x in the form of CDF of standard normal distributed random variable. So, such a model is going to be called it as a probit models. And here the p of x is nothing but psi of a plus b x, where psi is defined in the form of CDF of standard normal distribution.
Sir, it is written as P of x takes the following form. Which form?
In this form, in terms of CDF of the
Okay. If this form is taken, then call it as probit form.
then this model is going to be called it as. So, whenever the p of x is going to take this form, then such a model is going to be called it as a probit models. Again I am coming back to how to estimate A and B, that is A cap and B cap. So, when the explanatory variable y has only two possible values, we can easily find the estimates. Otherwise, in general the estimates of A and B are complex and one can use the software. E power B cap, that is going to be call it as a odds ratio. It represents the constant effect of the predictor x on the likelihood that one outcome will occur. That is called the odds ratio, that is E power B cap. So, once you get the estimate of B, then you can find the odds ratio, that is E power B cap. The interpretation of odds ratio depends on whether the predictor is categorical or continuous. So, odds ratios that are greater than 1 indicate that the event is more likely to occur. The odds ratio is E power minus B cap. If that value is greater than 1, then it indicates that the event is more likely to occur as the predictor increases. Suppose odds ratio that are less than 1 indicate that the event is less likely to occur as the predictor decreases. As the predictor increases, sorry. So, the odds ratio that is less than 1 indicates that the event is less likely to occur as the predictor increases. Now, we can compute what is the confidence interval for the B. That is you can with the given level of significance alpha, you can able to find the confidence interval, that is beta cap plus or minus z alpha by 2, the standard error of beta cap. So, all these notations we have already defined in the lecture 1. What is the standard error of beta cap? Instead of B cap, we have used beta there. Here I am using in the form of A plus Bx. In the regression and the correlation, we have discussed beta naught plus beta 1x. So, both are one and the same. So, we can find out the confidence interval with the alpha level of significance for the slope B is possible. Similarly, you can find the confidence interval for odds ratio, that is E power beta cap, with the given level of significance alpha, that is E power B cap minus z alpha by 2 standard error of B cap, comma E power beta cap plus z alpha by 2 standard error of B cap. We can go for hypothesis testing for the regression coefficients also. For example, you can take a hypothesis, a null hypothesis that the coefficient B takes a value 0 or not. The alternate hypothesis is B is not equal to 0. So, this test is called a walled test. One can create the test statistics, that is a standard normal distributed random variable by beta cap, sorry, B cap divided by standard error of B cap. So, this is going to be a standard normal distribution. So, one can apply all the 5 steps to conclude the null hypothesis will be rejected or not based on the sample information and the given level of significance, or you can use the p value also. Whatever we have explained till now with the single explanatory variable. That means whenever you have a single explanatory variable, you can estimate the regression parameters, that is both A and B. and you can go for 95% confidence interval or any given level of significance alpha, you can go for confidence interval for the regression slope, that is B, and also you can go for a significance test for the null hypothesis that B is equal to 0. Not only that, you can identify and interpret the odds ratio and the 95% confidence interval for the odds ratio also. Odds ratio is nothing but e power b cap. So, you can go for confidence interval as well as the hypothesis testing. Oh, sorry, not the hypothesis testing. We can go for find out the interpretation of a odds ratio as well as the confidence interval. Whereas for the slope, you can go for confidence interval as well as the null hypothesis testing. For the B, you can go for the confidence interval as well as the hypothesis testing. For the odds ratio, you can interpret what is the meaning of odds ratio as well as what is the confidence interval for the odds ratio. Whenever you have a more than one explanatory variables or several explanatory variable, you can extend the concept what we have discussed with the single explanatory variable in the same way. You can estimate the regression parameters. So, we can go for null hypothesis that all regression slopes are 0. Also, we can go for 95% confidence interval for the regression coefficients, and then you can go for null hypothesis that each of the regression coefficient is 0. You can go for hypothesis testing with the null hypothesis that each of the regression coefficients is 0. Finally, we can identify and interpret the odds ratio and the 95% confidence interval for the odds ratio for each explanatory variable, because we have several explanatory variables. For each variable, one can study the odds ratio. So, now we discuss the review problem on this topic. Question number 1. If coefficient of correlation are x y, that is 1, then there are 3 options. Regression lines become identical, perfect linear correlationship is observed, all of the above. So, the correct answer is C, all of the above. That means if the coefficient of correlation is 1, then regression lines become identical as well as perfect linear correlationship is observed. Question number 2. The coefficient of correlation is the dash of coefficients of the regression. There are 4 options: reciprocal of the product, arithmetic mean, geometric mean, harmonic mean. The correct answer is geometric mean. The coefficient of correlation is the geometric mean of coefficients of regression. Question number 3. Which one of the following is true for the coefficient of correlation? There are 4 options. The first option is the coefficient of correlation is not dependent on the change of scale. Second option, the coefficient of correlation is not dependent on the change of origin. Third option, the coefficient of correlation is not dependent on both the changes of scale as well as origin. Fourth option, the coefficient of correlation is depend on both the changes of scale as well as origin. So, the correct answer is C. That means the coefficient of correlation is not dependent on both the change of scales, the changes of scale as well as the origin. Fourth question, if the values of two variables move in the same direction, then there are two options. First option, the correlation is said to be negative. Second option, the correlation is said to be positive. So, the correct answer is B, the correlation is said to be positive. That means if the value of two variables move in the same direction, then the correlation is said to be positive. Fifth question, which one of the following techniques is an analysis of the relationship between two variables to help to provide the prediction mechanism? There are four options: standard error, correlation, regression, estimation. The correct option is regression. So, now question number 6. Suppose a professor would like to use the number of hours studied to predict the exam score that students will receive in his class. He collects the data for 20 students and fits a simple logistic regression model. What is the null hypothesis in this case? The answer is there is no statistically significant relationship between hours studies and the exam score. Question number 7. Assume that you have a fair coin in your possession, which I aim to find out the odds of getting heads. What would be your calculated odds? Would the odds of getting head be 0? Option B, would the odds of getting odd head be 1? Option C, would the odds of getting head be 0.5? So, the correct answer is B, would the odds of getting head be 1. With this, we are completing the lecture 3 of analysis of correlation and regression. Thank you.